How's it going, everyone? Hope you all are doing all right. All right. Well, let's go ahead and get started. First thing is, do we have any questions over the homework from last time? Okay. Well, please let me know if you do run into any questions. Make sure you let me know, and either I can point you in the right direction via email, or if it's like a more serious concern, then I can certainly create a video for that particular homework problem or set of homework problems, just working through one or multiple parts of a problem and showing you how to work that out. So, all right. So last time we left off in section 7.3, which is on the shell method that we were talking about. Here we are. So, let's start again with the kind of the fundamental elements of the shell method before we dive into some more examples. So for the shell method, we said that the volume, in this case, is based on the following formula. Okay. And the idea is we have a bunch of concentric cylindrical shells kind of stacked together, kind of nested together, and by adding up all these different cylindrical shells, we're able to get the volume of the resulting object. So the formula 2 pi times radius times height is based on the circumference of each shell multiplied by the height, and that gives us kind of the outside area of each shell. So if we think of it, a shell as just the outside of a cylinder, not the top and the bottom, just the outside, then 2 pi times the radius is actually the circumference at the base. Then we multiply by height to get that total lateral area. And so that's kind of the basis for our formula here, where we say 2 pi times integral of r of x times h of x. Now our radius and our height, because we're looking at multiple shells kind of stacked together inside each other, the radius is changing from one shell to the next, and then they may have different heights depending on what function kind of forms that top edge. Now, I believe we used this example before, where we had y equals 2 over x, y equals 0, x equals 1, and x equals 2, and we're revolving about the y-axis. Okay. So we go ahead and sketch our graph. Now, 2 over x looks something like this, and that's on both sides of the origin. Okay. Y equals 0 is the horizontal axis here. X equals 1 and x equals 2 are right here, and so they end up forming an enclosed area right here. And so this is revolving around the vertical axis, the y-axis. Now, we said that r of x and h of x are these different components. R of x is the distance from the axis of revolution to each of these x variables from 1 to 2. And so for each of these x values from 1 to 2, that's how far that part of the graph is away from the axis, and so that's its radius as we rotate this figure around the y-axis. Okay, so if we took 1, x equals 1, would be a distance of 1 away from the origin, away from the y-axis, and we would make a cylinder of radius 1 as we revolve that around the y-axis. If we look at the opposite end at x equals 2, we're now 2 units away from the y-axis, so we'll have a radius of 2 units as we go around. And so if we think about the structure that is then created in this scenario, we get a circle, and then at 2 we get a larger circle, and then we certainly have a higher point in the middle than we do on the edge, and that is on both sides. It turned into a very busy drawing, so I apologize for that. That probably would make more sense without the axes present. But the idea is we have this curved face here, and that goes all the way around, and then we have this vertical component here at the edge. And that's the 3D figure that's created, and we're trying to find the volume of this figure. Now again, the idea is that we're going to get a cylinder for the very innermost part, and we're going to get a bunch more cylinders the further out that we go. And these will, as the further away that we go from the middle, we're going to get smaller and smaller height till we get to 2. So 1 will have the highest cylinder, and by the time we get to 2, we'll get the smallest cylinder. Well, shortest, but it'll actually be a lot wider as well. So that's kind of the idea. I just drew 4 cylinders here, But the idea is we have a bunch of cylinders nested together to create this 3D object. So there's just basically from 1 out to 2, there's an infinite number of cylinders in there, and that way the sum of these individual areas adds up to the volume of the resulting figure. Okay. That's the bad drawing portion of this question. Alright, so the question is now, how do we measure r of x? Well, the nice thing about r of x is it's usually just x, or x modified by the axis of revolution if it's not just the y-axis. And we'll do another example where it's not the y-axis, just to show how it's different. So r of x is just equal to x, because basically each of these x values from 1 to 2 is x units away from the axis of revolution, which is right on the origin. Okay. So if we picked 1, it's 1 unit away, so we'll have a radius of 1. If we pick 2, it's 2 units away, we'll have a radius of 2. And if we pick 1.5, it's 1.5 units away, and that'll be a radius. And so essentially the radius is identical to the x value in this case. For our height function, that is the function that forms the top edge here. In this case, we have y equals 2 over x, or h of x equals 2 over x. And our limits of integration, this is where it's fundamentally different from the disk or washer method from section 7.2. And that is that for a shell method, we only choose the values of x that the shaded area exists between. So we're only creating cylinders from 1 to 2. We actually are going to have an empty space through the middle of this thing. Okay, we have an empty space in the middle. But then we have this solid region that exists from 1 to 2. Because that's where our cylinders are being created. That's the limits of integration that we're going to use, 1 to 2. Okay. So that's our volume, or that's our integral that we'll use to calculate this volume. And I think this is basically where we left off last time now. So x times 2 of x, very conveniently, this works out to be just 2. The x's cancel out. So we go ahead and go from there. We can go ahead and integrate 2. We know the integral of 2 is 2 times x. And then if we plug in our limits, if we plug in x equals 2, we get 2 times 2 is 4. X equals 1. 2 times 1 is 2. And those are subtracted. So we end up with 2 pi times 2, which means we have a volume of 4 pi for the resulting object of revolution. Okay, are there any questions on that? Alright, that was a problem I made up. Let me go ahead and pick several out of the book that we can work. First of all, on page are we on? 470. Let's go ahead and look at number 6 to begin with. Now 6, they give us y equals 1/2. This is x squared plus 1. And they actually give us a graph here, which is nice, because we don't always have a graph provided. Let's see, this will be a 2. So we know this curve right here is y equals 1/2 x squared plus 1. What is this top edge? What line represents this top boundary here? Y equals 3. So we'll use y equals 3 as that top boundary. And so when we calculate the height, h of x, the height will be this component here, which is basically the distance from the top edge of the region to the bottom edge of the region. Oh, by the way, we are going around the y-axis. So for h of x, we'll take the top edge, you'll always do top minus bottom, which is 3, minus the bottom edge, which is 1/2 x squared plus 1 in parentheses. So h of x would equal 3 minus the 1 would be a 2, minus 1/2 x squared. R of x is once again just x because we're going around the y-axis. After we do this problem, I'll talk a little bit more about R of x, because this tends to be a little bit more of a confusing thing for a lot of students. Okay. So we have h of x, we have r of x. What limits of integration are we going to use for this shaded region? Again, we choose the limits of integration based on the values, the x values in this case, between which the region exists. So our shaded region, we can see, is between two numbers. In this case, it is between 0 and 2. So we'll use 0 to 2 as our limits of integration. Okay. Now, just like with the disk and the Washer method problems, the largest portion of the problem, or the most difficult portion of the problem, is just getting to this point where we can write a formula for the volume in an integral. Okay, we established what h of x was, we established what r of x is, and we found the limits of integration. Those are the three different things we really need to identify in order to complete our shell method integration. And so now that we have everything we need, we can go ahead and perform the actual integration. So I'll just go down So inside of our integral, we'll go ahead and distribute our x first. So that'll be 2x minus 1/2 x cubed. Once we get rid of that multiplication, now we can go through and integrate the individual parts. So integral of 2x, we know that's x squared. What is the integral of 1/2 x to the third? So 1/2 x to the third, we add 1 to the exponent, so it's x to the fourth. And then we divide by 4, which, if we put another 4 in the denominator, that actually multiplies by the other 2 that's there. Close, it is x to the fourth, but it'll actually be a 1/8. And that's where we have to be careful. Because we add 1 to make it x to the 4, and then we divide by 4, the 4 being on the denominator with the 2, those end up multiplying together to give us the 8. Okay, so we plug in x equals 2. Now 2 squared would give us a 4. 2 to the fourth would be 16, and then times 1 over 8 would give us a 2. And 0 just results in a pair of zeros. So we end up with 2 pi times 2. So our volume ends up being 4 pi. Which I think was the answer to the last one. So it's kind of a nice, interesting coincidence. This one's a little bit easier to explain because the object that is created is basically, is it a hemisphere? It's not a hemisphere. Sorry, that's my bad. It's not a perfect sphere or half sphere. It's just a coincidence with the value. Okay. Let's look a little more about, look at a little bit more at this r of x value. Okay. For instance, we have a shaded region right here between 1 and 3, and maybe it's just a triangle. But we have some different axes that we want to revolve it about. We have the y equals -1 axis, the y equals 0 axis, the y equals 1 axis, and the y equals 5 axis. Okay. Let's say, now we said if we go about y equals 0, r of x is simply x. Because going around 0, that means the x value is exactly the distance of that value from 0. Okay. Now, if we revolve this figure around -1, r of x would equal x plus 1. If we revolve about y equals +1, r of x would be x minus 1. And lastly, if we revolved about y equals 5, r of x would be 5 minus x. Okay. In general, the pattern for r of x is x minus the axis, or axis minus x, depending on which one is to the right of the other. Okay? So either x minus the axis or the axis minus x. And we said it depends on which one's to the right or the other. It's always right minus left. So let's see how that stacks up with what we said here. Our shaded region is here, y equals 0 is here, so our shaded region is to the right. So we take x minus the axis, x minus 0, which gives us x. If our axis is y equals -1, then our shaded region is to the right. So we take x minus -1, which ends up being x plus 1 when we resolve the two negatives. If we take this shaded region and revolve it around y equals 1, the shaded region is still on the right, so we would take x minus the axis, which is 1, x minus 1. And finally, if our axis is all the way over here to the right of our shaded region, y equals 5, then we would take this value 5 and subtract x representing the shaded region, so we would get 5 minus x for our radius function. Hopefully that makes a little more sense after that. Alright, so let's look at problem 24 on page 470. We're given y equals the square root of x, y equals 0, x equals 4, and the graph is going about x equals 6. Now again, the first three equations they give us should uniquely define an enclosed region in the plane, and then we'll revolve it around this axis wherever that happens to be. Now, square root of x is essentially the top half of a parabola that goes up and over to the right. And it's going to stop at 4. And we also have y equals 0, so we have this boundary, and the graph. So we can see that this is our shaded area that ends up being enclosed by the three equations. X equals 6 is over here. This is our axis of revolution. First of all, what would we say is r of x in this case? Based on what we just saw on that last page. So again, we have our axis to the right of our shaded region, and we said the rule is whatever's on the right, we subtract the left. Now the shaded region itself represents all the different x values that we use here. So if we take our axis minus x, we'll use 6 minus x as our radius. Let's think about that. If we end up using an x value of 4, for instance, okay, at x equals 4, how far are we away from this radius? Well, 4 is 2 units away from 6. 6 minus 4 gives us a radius of 2, so when we take this part of the graph and revolve it around this axis, we'll create a cylinder of radius 2. If we pick x equals 3, 3 is 3 units away from 6. So if we plug in x equals 3, 6 minus 3, we still have a distance of 3, so it's a radius 3 going around that axis. At x equals 2, we're now 4 units away from 6. 6 minus 2 is 4. So we have a radius of 4 going all the way around. X equals 1. We're now 5 units away from the axis of revolution. 6 minus 1 is 5. That's how that corresponds to what we're seeing. And at the other end of the shaded area, x equals 0, we're actually 6 units away from the axis of revolution. So if we plug in x equals 0, we get a radius of 6. Okay. H of x is a little bit easier. In this case, h of x is basically the vertical component of this shaded area. So when we talk about the vertical distance, it's always top minus bottom. The top edge is based on this y equals square root of x curve, and the bottom edge is y equals 0. It's right on the axis. So we take the top square root of x minus 0 on the bottom, and so we just get square root of x as our height function. The last thing we need are the limits of integration. And again, the limits of integration basically are the ones that kind of outline where the shaded region starts and where the shaded region ends. Now this area we have starts at x equals 0 and stops at 4. So we're going to integrate 0 to 4. Okay. So our volume is 2 pi integral 0 to 4. We have 6 minus x times the square root of x dx. And that is the proper setup for our volume by cylindrical shells in this case. This ends up being a little bit more difficult of a problem as far as the integration goes, because we had that square root of x that's present and is not being squared. It's just a square root of x, so we have to deal with it. So go ahead and distribute our square root of x. And so I would recommend in this case, we have square root of x present here in both terms now. I would recommend we switch to a fractional exponent rather than a radical. For instance, we know that square root of x is identical to x to the 1/2. So we can change that to 6x to the 1/2. And if we have x times x to the 1/2, that'll be x to the 3/2, combining those together, adding the exponents. So by writing the two expressions, or the two terms, into this form with the fractional exponent, we can go ahead and do a power rule integration like we would hope to here. This is the only way we can succeed with these two integrations. Excuse me. Now 6x to the 1/2, we want to go ahead and integrate that. So again, we start by adding 1 to the exponent. 1/2 plus 1 makes it 3/2. And we then we have x to the 3/2, and we divide by 3/2. But again, rather than dividing by 3/2, let's multiply by its reciprocal. So we have 2/3 x to the 3/2. We'll actually be able to simplify that pretty nicely there. In this case, adding 1 to 3/2 makes 5/2, so we'll have x to the 5/2. And again, instead of dividing by 5/2, we'll multiply by its reciprocal, 2/5. Alright, so 6 times 2 is 12, divided by 3 makes 4. So this number right here is just a 4. And then we plug in x equals 4. 4 to the 3/2 power. That means we cube it and take the square root. Or we could take the square root first and then cube it. So the square root of 4 is 2. And then 2 cubed is 8. So we end up with 4 times 8. If we plug in the 4 here, 4 to the 5/2 power, again we need a square root, and we also need to raise it to the 5th power. And these can happen in either order. It's easier to take the square root of 4 first, though, which is 2, and then raise 2 to the 5th power, which is 32. Again, the 0 results in a pair of zeros, so we're okay there. So looking at what we end up with, we end up with 32 minus, this will be 64/5. And if we actually combine those, that's 5 times 32, which is 160, minus 64 makes 2 pi times 96/5. And we can then multiply 2 times that top number, so it's 192 pi over 5. This time the integral and the evaluation of that integral is a little bit more involved. But again, the main thing that we always want to focus on is making sure at the outset of the problem we get the correct radius, the correct height, and then the correct limits of integration. That's always the most important part, because if we've set up our integral correctly, we're going to have a lot more success based on that, of course. We'll move on to, let's Let's look at 30. Same section still. We have y equals 10 over x squared, y equals 0, x equals 1, and x equals 5 as our boundaries. So we'll go ahead and create our graph first. I'll go ahead and put it underneath. Now 10 over x squared looks like this. Y equals 0 is the horizontal axis, x equals 1, and x equals 5. So that's going to enclose this region here. Now, yeah, we're okay. For this problem, I'm just going to set up the integrals. We won't actually carry them through because most of them will be pretty straightforward. But let me know if you do have any questions on this. So, part A, we want to go about the x-axis. Part B, we want to go about the y-axis. And part C, we want to go about y equals 10. Okay. Now, we should go ahead and figure out what these values are on the y-axis, where the shaded area ends. For instance, they're both on this curve, y equals 10 over x squared. So if we just plug in x equals 1, we should be able to get the y value here. So at x equals 1, 10 over 1 squared gives us a 10. And at x equals 5, 5 squared is 25. 10 divided by 25 would be 0.4. So this graph is actually a lot more tall than it is wide. It's just how I drew it. So it's not the scale, let's say. So we know where the x-axis is. X-axis is horizontal. We have our shaded area. I'll go ahead and draw it a little bit larger this time. That's 1, that's 5, and that's 10. And we want to go about the x-axis in part A. Now, let's think about the best choice as far as what we can do here. Because at this point, the book wants us to consider not just the shell method as a possibility, but also the disk and the washer method. Now, our shell method, we said, if we want to use x variables, let me write this over here. If we want to use x variables, then we use 1, a disk or washer method with a horizontal axis, or 2, we use a shell method with a vertical axis. So looking at part A, the question is immediately, which of the three methods, disc, washer, or shell, would work best for part A? Disk? Yeah. The reason we would choose disk here is, first of all, we notice that our axis of revolution, the x-axis, is horizontal. So if we want to keep using our x variables, we can use the horizontal axis, which means we have either a disk or a washer. Now, from here, we look at the shaded region, and if we revolve this object around this axis, is it going to be one solid object, or is there going to be a hole through the middle that we have to account for? Well, because our shaded area is right up adjacent to the axis of revolution, they're actually touching. In this case, we know we can go ahead and use a disk because there won't be any empty space that gets revolved in this scenario. So yeah, we'll use a disk here. Our radius, in this case, is our vertical component, which is just the vertical distance between the function and the axis. So for our volume, we know we have pi. What limits of integration would we use? Again, we're just working with x variables. Mm-hmm. 1 to 5. Yeah, we go from the left edge to the right edge, 1 to 5. And then we just have our radius function squared, which is just the curve itself. So 10 over x squared, parentheses, squared, dx. I figure what you meant. Okay. So yeah, because we have a horizontal axis, we know we can use either a disk or a washer method and still use the x values, which is a nice goal, I think. And because the shaded region is flush against the axis of revolution, we know specifically we can use a disk. And so we'll integrate from 1 to 5, our left edge to our right edge. Our radius is just the distance from the axis to the opposite side of the figure, which is the y equals 10 over x squared function. So our radius is 10 over x squared, and as part of the formula we do square that, and then we'll integrate with respect to x. Alright, so for question B, we have the same figure, same shaded region. One, 5, 10, and this time we're going around the y-axis. So if we're going around the y-axis, which method would we like to use in this case? Shell, right. Because we have a vertical axis, we know that if we use a shell method, we can just stick with our x variables and not have to worry about changing everything to y's. In fact, this would actually be a much worse problem if we did a disk or washer method, because our figure here is actually what we call a concave figure versus a convex figure, because it actually goes into itself, and we would actually have to split this up into multiple integrals if we were to do a washer method in this case. And that's the other thing. This would be a nice shell method as it is with the vertical axis, but if we wanted to use disk or washer, we would have this empty space between the shaded area and the axis. It would be a washer method also, which increases the level of work. Okay. Since we're going around the y-axis, what would be our radius function in this case? It's okay if you're still having a little trouble with that. But around the y-axis, the radius is always x. Okay. So the idea is that x represents the location of the shaded region, and we always take whatever's on the right minus the left. X minus an axis of 0 just gives us x. Our height, in this case, h of x, is just the vertical component between the top and the bottom edge, which is actually identical to what we used before in the part A, except in this case it was the radius. So we'll use 10 over x squared for our height. And the last thing is limits of integration. What would those be? Again, we're focusing on using our x values every time, so we want the limits on the x-axis. 1 to 5, right. Okay, so that would be our setup for that integral. Now C, again we have our same shaded region. One, 5, and we have this is 10 right here at the top, and this time we're actually using 10 as our axis of revolution, y equals 10. Now again, in this particular case, would we like to use a disk, a washer, or a shell? Right? Washer? I really like this particular example because it shows us the 3 different scenarios. You know, depending on which axis of revolution we have might have a disk, we might have a shell, and we might have a washer method, and this shows us all 3 possibilities. The reason we would choose washer is, again, we have a horizontal axis, so in order to keep using our x variables, we would want to use a disk or a washer. But now we look at how our shaded region, is it completely flush against the axis of revolution, Well, no, because there's this empty space in between this curve and the axis itself. So with that empty space there, we would have to complete a washer method instead of a disk method. Now, we know with the washer method we actually have to find two different radii. So capital R of x is our radius, or that's our distance from the axis y equals 10 to the far side of the shaded region. What would capital R of x be in this case? So we're looking at the distance from the axis all the way to the distance to this side here. Now these are actually parallel lines, so the radius, the distance between them, is actually a constant value, and that'll just be 10. In general, washer methods tend to be a little bit more involved than the disk method. Even though they kind of describe similar things, we have to find two different radii for the washer method, and if our axis is not where we normally expect it to be, it further complicates things. Little r of x now is this distance from our axis of revolution to the nearest edge of the shaded region, which is the top curve. And we take the top minus the bottom. Top is 10, bottom is 10 over x squared, and we subtract. Okay. And so finally we can set up our volume. One of the interesting things here is that in all three of these integrals we used 1 to 5 as our limits of integration. So that's at least consistent. We always keep using the same two values. What changes from there is how the method then follows from that. Which formulas do we use for the disk or the shell or the washer method? Now washer is a little bit more complicated. As we said, we take capital R of x squared minus little r of x squared, and then integrate the difference. Okay. I think that page right there is a really nice summary of the difference between the disk, the shell, and the washer method, and it shows us how to utilize that in each of those instances. What I'll probably do is this page in particular, I might go ahead and take a screenshot and upload that to Canvas so you can look at it in more detail. So I will make sure to do that after class today. Okay. Now I think that's all that we're going to do out of section 3. Alright, so let's move on to section 7.4. Which is on arc length. Now arc length, basically the idea behind arc length is, let's say that we have curve, and we actually have endpoints rather than arrows, sorry, and it starts at point A and it goes to point B, from x equals to A to x equals B. So when we talk about the arc length, and this is a function f of x that defines the curve, the arc length is the length that we would get by taking this part of the function from A to B, stretching it out, and then measuring how long the result would be. So the arc length is the length of the curve if it were stretched out as a straight line. And specifically, I guess, would be the portion of the curve that we're looking at. Another way that we could think of that is if we're traveling along a road that is winding a little bit, like we see here. If this function f of x represents the path that a road follows, and we drive from point A to point B, how far will we actually have driven along that road? And that would be our arc length. That'd be the length of this if we stretch it out as a straight line, basically. Hopefully that makes sense. So we have a formula, of course, associated with the arc length of a function. We'll call this value capital L, I believe. The book uses S, which is fine. We can use S. I like to use L since it actually is a length. But the reason the book uses S is the length of an arc of a circle, basically. And so for our arc length, this will be the integral from A to B of the square root of 1 plus f prime of x squared, and that's all under the square root, and then integrated with respect to x. This one's nice because we just have one formula for arc length, and this is it. And theoretically, even if we had f of as a function of y instead of x, we'd still apply it just as we see it here. We'd just put f prime of y and dy instead of f prime of x and dx. That'd be the only difference. And we would use our y limits instead of our x limits. It's not a major conversion to go from x's to y's in this case, so we can just use whichever one we're given. So on page 481, let's go ahead and look at number 12. Here we're given the equation y equals 3 over 2 times x to the 2/3 plus 4, and in brackets after that they have 1 comma 27. What this is telling us is these are the limits of integration we want to use. So we want to find the length of this arc created by the function y equals 3/2 x to the 2/3 plus 4. And we want the length of the arc from x equals 1 to x equals 27. First of all, what is y prime in this case? Just taking the derivative. X to the negative 1/3 plus 4. What's the derivative of 4? Remember, taking the derivative, not the integral. Integral of 4 is 4x. The derivative of 4 is 0. Good. Yeah, so it'll just be x to the negative 1/3. And this is one of the things that make a class like Calculus 2 a little bit more difficult, is now we're in the same question using both derivatives and integrals, so we always have to be mindful of which direction we're going with our function. Are we differentiating or are we integrating? So, yeah. Okay. So, y prime, this will be plugged in right here. So our arc length will be integral 1 to 27. And we have a square root of 1 plus x to the negative 1/3 in parentheses squared dx. Okay. Let me move that up. Now, if we go ahead and square that term, that would actually be x to the negative 2/3. Now, because if we have x raised to a power raised to another power, we just multiply those two powers together. So Negative 1/3 times 2 is negative 2/3. Alright. So the question is from here, how the heck are we going to integrate this thing? Well, the arc length problems, there only tend to be a limited number of ways that they could actually be integrated. Depending on the function that they give us, it could be that we end up with just a simple constant under the radical here. In this case, we have a constant plus some other term. So in this scenario, my recommendation is that we go ahead and get a common denominator for the different terms that we have. Now, part of the issue is that we have x being raised to a negative exponent right here. X to the negative 2/3 is the same thing as 1 over x to the 2/3. Let me write that down over here. This is going to be a little bit of an involved approach, but this is kind of our standard approach that we use for arc length questions. We want to get a common denominator here, and so only one of our terms has a denominator in the first place, so we know that's the common denominator. So we'll put x to the 2/3 on the bottom. We know the second term here doesn't really have to change. It's 1 over x to the 2/3. Now, what does the 1 have to turn into here in order to have that common denominator? Well, if this is a 1, in order to get a common denominator, we'll have to multiply by x to the 2/3 on top and on bottom. So 1 times x to the 2/3 is x to the 2/3. Okay. Now, you still may not be sure how the heck this thing works out from this point, which is fine. This one, like I said, is pretty weird. But the issue is, we actually have a fraction under the square root. Now remember, our property of square roots says that if we have a square root of a quotient, then that's equivalent to the quotient of the square roots. Meaning that this square root that's here over the whole fraction, we can basically split it up into two different parts where the square root of the numerator over the square root of the denominator. Now, the reason that we would want to do that is that if we've done everything properly to this point in an arc length problem, this denominator should be a perfect square, and it is. Now, when we think about the square root of x to the 2/3, it might be better to say x to the 2/3 raised to the 1/2 power, because we know the square root is the same thing as the 1/2 power. And again, our property is with x raised to one exponent and then to the other, we multiply these two exponents together. So it's 2 times 1 on top, 3 times 2 on bottom, so it ends up being 2 over 6, which is x to the 1/3. Okay. Now you may be wondering, what kind of progress have we made at this point? Well, we've actually reached an important threshold here, because now we can complete our u substitution. When we think about what in this problem should be a u, typically we think of something where we have like multiple terms, and it would be nice if we only had one term. And we can see that's going to be what's under the radical right here, x to the 2/3 plus 1. You may be also thinking, why haven't we done substitution yet before this? Well, the problem with substitution is that whatever we let u equal, we have to have its derivative also present in the problem. And until we got to this point, we did not have the derivative present. So we take the derivative of u, which if we take the derivative of x to the 2/3, we multiply the 2/3 in front, and then we raise it, and then we subtract 1 from the exponent. 2/3 minus 1 leaves us a negative 1/3 du. Okay. Now, x to the negative 1/3, that has a negative exponent, so we can think of it as 1 over x to the positive 1/3. This is x, I'm sorry, dx here. And so now we see 1 over x to the 1/3 dx, that's what these two terms represent right here. So we have both of those terms. What we don't have is the 2/3, so instead we'll say 3/2 du is equal to 1 over x to the 1/3 dx. Okay, so this will be a u under the square root still. The square root's not gone. We only substituted for what was inside. We did not include the outer square root here. If we did, it wouldn't work because we would no longer have the proper derivative. And then our derivative of this term is basically a multiple of x to the negative 1/3, which is right here. This is x to the negative 1/3, since it appears in the denominator. So completing our substitution, we're going to get 3/2 integral 1 to 27 square root of u du. Okay. Are there any questions on that? As you can see, these are not easy problems. More than likely what I'll do is I'll split up the test into multiple parts, where we have part of the test be completed in Canvas as an in-class portion of the test, and then I'll give you a separate portion to take home to work on. Now what I would prefer that the ArcLink question be on the in-class portion, but what I may do is just have the in-class portion be on the first 3 sections, and then the take-home portion be on the remaining sections. I'm going to think about that, though. We'll see how it goes. There may be another section I want to include in class. I'm not quite positive on that yet. So, and we're still a ways off from our first test. We still have 2 or 3 more sections to cover, I believe, after this one. I'll make sure I get y'all a schedule out tomorrow. And then first test I would anticipate maybe 2 weeks from today. Think about that. Just keep it in mind. Keep studying and getting ready for it. So, anyway, let's continue this problem. Now, we know rather than integrating square root of u, we would prefer to integrate u to the 1/2. And so that would give us u to the 3/2. And we would divide by 3/2 or multiply by 2/3. Now at this point, we can actually cancel out the 2's and the 3's that are on the outside. The extra 3/2 we picked up from the u substitution, and the 2/3 that we picked up from this integration, those cancel each other out, so we just have u to the 3/2. Now we'll go back in and plug in our u, which u is equal to x to the 2/3 plus 1 to the 3/2 power from 1 to 27. Yes, we will have I'll at least give you a list of review problems, but essentially that will be a practice test when I give you all that. Yeah. Okay. So we plug in 27. Now 27, we want to take the cube root and then square, or we could square 27 and then take the cube root, whichever way we want to go. You can do it on our calculator, or we can do it by hand. Now the cube root of 27 is actually 3, and then 3 squared is 9. So we end up with 9 plus 1 makes 10 to the 3/2 power. Minus, if we plug in x equals 1, now 1 to any power is 1, plus another 1 makes 2 to the 3/2 power, and so that is really all that we can do with our length. We could also approximate that with our calculator and say 10 to the 3/2 minus 2 to the 3/2, and that gives us approximately 28.794. Okay. still have two more examples I would like to do. I don't know if we'll have time for both of them, but let's see how much we can get done. The next example would be problem 14 on that same page. Y equals, let's see, we have x to the, what's that, 7? Yeah, x to the 7 over 14 plus 1 over 10x to the 5th. And that's from 1 to 2. Okay. Now, again, the formula is, or the approach is, that we take the derivative of this and plug it into the formula. Before we take the derivative, though, let me rewrite this in a little bit different term. Notice that we can write it separately as a fraction times a variable expression. So this is x to the 7th times 1 over 14, we could say. And this is 1/10, and if we take the x to the 5th, move it up, that would be x to the minus 5. The reason we would like to use x to the minus 5 instead is it's easier to differentiate that with a power rule than to use it while it still is part of the fraction. So y prime, we know we're going to multiply by 7 and then decrease the exponent by 1. Here, we're going to multiply by -5 and then decrease the exponent by 1. Here, it's important that since it's already negative, when we're decreasing it by 1, it goes further negative. Alright, and so that's actually just 1/2 x to the 6 minus 1/2 x to the -6 if we go ahead and reduce those fractions. So that's y prime. So our arc length is the integral from 1 to 2, and we have 1 square root and then 1 plus this term in parentheses squared. Okay. Now that may seem a little daunting. But it is just a FOIL operation if we think about it, because we're going to take this expression and multiply it times itself. So we'll just FOIL this times itself. So if we take the first term and multiply it times itself, that would be 1/2 x to the 6th times 1/2 x to the 6th. 1/2 times 1/2 is 1/4. X to the 6th times x to the 6th is x to the 12. Now, if we multiply these together, what is x to the 6th times x to the -6? So we have x to the 6 times x to the -6. We add their exponents when we multiply them together. So it ends up being x to the 0 and then anything to the 0th power will just give us a 1. So we get x to the 6th here times x to the negative 6 will just be a 1, but then we also multiply 1/2 times negative 1/2, which is negative 1/4. And we get that for the inside and the outside part of FOIL, so I have it twice. And then the last part, still squaring this binomial, is we square the last term here, which is going to be a positive 1/4 x to the negative 12 dx. From here, let's combine our like terms, and what I'm also going to do is go ahead and rewrite these to a point. For instance, we have 1/4 x to the 12th. We could make that x to the 12 over 4. Our constants, we have 1, a minus 1/4, and a minus 1/4. So that's still a positive 1/2 when we subtract those. And then we have 1/4 x to the negative 12, which is 1 over 4x to the 12th dx. The reason I went ahead and wrote it like this is we go back to the method that we talked about last time, which is to get a common denominator. In this case, the common denominator, let's see, we have a 4, a 2, and a 4, so we'll need 4 as our common denominator. We'll also need an x to the 12 to account for this other term. So basically this is the common denominator right here. This term will have to be multiplied by x to the 12th. This middle term will be multiplied by 2x to the 12th. And the last term multiplied by 1. So on top, x to the 12 times x to the 12 is x to the 24. Here we need 1 times 2x to the 12th on top. And then we still have plus 1 and then dx. Now, we get to this point, and we actually have a perfect square on the denominator. So we'll be able to completely take the square root of this expression on the bottom. But what's interesting about this problem now is that we actually have a perfect square on the numerator also. Now, this may not look like a perfect square, but we think of it as a binomial squared. So if we wanted to factor this, x to the 24th plus 2x to the 12th plus 1, it turns out that our numerator could be rewritten as x to the 12th plus 1 in parentheses squared. So what I've done in this step is basically taken both the numerator and the denominator and expressed them as terms that are being squared. So here, if we were to FOIL this back, x12 times x12 is x24, x12 times 1 inside and x12 times 1 outside means we have 2x to the 12th, and then 1 times 1 is 1. So lastly, because our square root is now applied to both the top and the bottom, the square root now cancels out both of the squares of the terms inside. So we don't even have to do a substitution this time. We just take the square root of each term. So we've completed the square root. Now, we still need to be able to integrate this, and we're not at a point yet where we can integrate. But because we have one term on the denominator like we have here, let's just split this up into two separate terms. So we have x12 over 2x to the 6 plus 1 over 2x to the 6. Let's see, so x12 over x6, that'll be 1/2 x to the 6th, and this will be 1/2 x to the negative 6. So what we'll do is if it's x to the 6th in the denominator, we'll bring it up to the numerator and have a negative exponent. Now, you may say, hey, this looks familiar. Well, it does look familiar. That was our derivative of y prime. Almost, because here it's minus and here it's plus. So it's going to have almost exactly the same integral. It'll just have a different sign between the terms. If we integrate 1/2 x to the 6, we know it'll be x to the 7, and then we'll divide by 7 and make it a 1 over 14 x to the 7. Same thing here, add 1 to the exponent. Negative 6 plus 1 is negative 5. And then we divide by negative 5, which multiplies the 2. So we end up with a negative 10 on the bottom. So we could say that we end up with x to the 7 over 14 minus 1 over 10x to the 5th, and that's from 1 to 2. That may also look familiar because that's the original problem that we started with. We had x to the 7 over 14 plus 1 over 10x to the 5th. We have almost an identical term here, but now the sign is negative between them. And that's not a coincidence. For this type of a function, that's going to happen every single time. So it's a nice way to check that we've done the problem correctly, is by recognizing that this is almost identical to what we started the problem with, but it does have a different sign in between. Now we still need to complete the integration. So again, we have x to 7 over 14. If we plug in 2 to the 7th power is 128 over 14. And that certainly reduces, I don't know to what. And then 2x to the 5th, plugging in 2, we get 32 times 10 is 320. So minus 1 over 320. We plug in the 1, we just get 1 over 14. Plug in the 1, we get 1 over 10. So 1 over 14 minus 1 over 10. Okay, now I don't know about you, but I have a calculator that does these fractions very quickly. So we'll do 128 over 14 minus 1 over 320 minus 1 over 14 plus 1 over 10. It gives us a huge number, 20,537 over 2,240. Nine and 377 over 2,240. Okay. So that would be our answer then. All right. Now, those fractions came out a bit weird there because we didn't have a great common denominator between these two. 14 and 320 certainly have a 2 in common, but I think that's the only number they have in common. So we end up taking the 7 from the 14 and multiplying by 320 to get 2240. Anyway, for homework, let's see. First of all, on page 470, go ahead and look at five, seven, 9, and then 29. And on page 481, look at 9, 11, 13, and 15. Okay. So that's all I have for you today. We're kind of out of time anyway. I know that these problems will take a while. I mean, there's no way to soften that blow. 9 is actually relatively short because of the way things work out, but the rest of them are going to be pretty crazy. So just do what you can on those. If you do run into any questions, please send them my way. I know that Monday is a holiday, but it doesn't really affect us, but it does mean that everyone gets a 3-day weekend, at least from school. If you still work, I know you probably don't really get any. No, you hopefully get Labor Day off. I hope you do, but not everyone does, I know. But anyway, everyone, take care of yourselves. Have a good rest of the day, and I will talk to you on Tuesday next week. Take care.